those those kind of problem in a standard form. So we will also talk about those approach as well. So first I am going to introduce convex optimization problem. Then I will talk about equivalent optimization problem. So what is happening that what I mentioned that uh, a problem that one is satisfying the condition that minimizing a convex function over a convex set means a convex optimization problem, but that problem is not in a standard form, so we can reduce that into a standard form by using some kind of transformation. Then I will talk about optimality condition. For that means here in case of convex optimization, local equal to global, that means local optimal solution of a convex optimization problem, it happens to be global optimal solution as well. So that's way convex program of convex optimization problem is very famous, and these are having a lot of iterative method to find the solution of this one. So local equal to global, I have written again local, so call it local equal to global. So that concept it is coming here in case of convex optimization. Those things we will see, and also I will talk about proof of this concept as well. So I want to go detailed proof of those things. I will give highlight of those things. So coming to convex optimization problem, uh, is first I would like to give a standard framework of convex optimization problem. So what is that? So we a standard framework of a convex optimization problem, it can be formulated as we have to minimize an objective function which satisfy the inequality constant. Remember that this one is inequality constant and the equality constant. Here, for being a convex optimization problem in a standard form, criteria is that the objective function must be convex, the inequality constant, the function involved in inequality constant, all must be convex, and the equality constant, here equality constant, it must be affine in nature. So we know that every affine function happens to be again a convex function, but in a standard form we are putting a very special criteria that equality constant always must be affine. If there is a equality constant which is not affine, simply we can reject that problem by saying that it is a non-convex problem. So you have to remember, and when you come to inequality constant, you have to consider that the involved constant function must be convex, and apart from that the objective function also must be convex. Now if you solve these equality and inequality, that means if you solve these inequalities, then you will get your feasible set. So feasible set of convex optimization problem, you can say that intersection of all level set defined by fi constant along with affine affine condition. So intersection of this one is coming with respect to inequality constant, and this set is coming with respect to equality constant, and both happen to be convex. So intersection of convex is again a convex. So due to the definition of feasible set of this convex optimization problem, the feasible set C always happens to be a convex set. So in short, you can simply say that again you are minimizing a convex function over a convex set. So your f naught is a convex function, and in short, you can say that x is coming from the feasible set C. All these big things you have just sorted it into a smaller form. That's saying that it is defining this set C, that feasible set C, and you minimize objective function, the convex objective function over the feasible set C. So it is taking a very general form of convex optimization problem, that minimizing a convex function over a convex set. That is the criteria. But overall, in a standard form, you always take this framework to solve convex optimization problem in CVX and other solver kind of thing. So often this problem also further we can write in a very compact form, because here we are having p number of equality constant. So we this equality constant we can jointly write as a matrix equation. So that's why compact form of the above equation you can write minimize a convex function f naught over this constant f of I is less than equal to 0, where I vary from 1 to m and ax equal to p. That means jointly you are writing all these affine equation or linear equation in the matrix form. So you know from it, this one is very much clear from linear algebra. So also there is important property that feasible set of a convex optimization problem is always a convex set. Now coming to few example of convex optimization problem, here I will discuss about few example. So for one example I will take that would be a convex problem, and another example would be a non-convex problem. So consider a problem where we are minimizing linear function minus 2 times x1 plus x2. Remember that this one is a linear function, so linear function is always a convex function. There is no issue. Now, subject to a single inequality constant, it is saying that x1 square plus x2 square less than equal to 3. So it defines a sublabel set in R2. So you can observe here, your objective function is what? Minus 2x1 plus x2. So it is a linear function. Due to that, it is a convex function, and convex function over Euclidean space R2. Why? Because it is a function of two variables. There are two independent variables x1 and x2. Similarly, you can observe that the constant function. Remember the constant function f1 of x. It is what? It is defined as x1 square plus x2 square minus 3. And that's why whatever in convex optimization in general framework, I had given condition that constant satisfy this kind of condition. F of x less than equal to 0. That means right hand side 0 is there. We don't put any non-zero things. So that's why here we observe three things. So that's why we have to normalize this one. This in the form of what? X1. This inequality we have to normalize in the form of a standard form. That means x1 square plus x2 square minus, if you bring 3 left hand side, then it becomes minus and less than equal to 0. So very fine, very nice. It satisfies equality constant, and also we observe that the function x1 square plus x2 square, it is a convex quadratic function. It is a quadratic function, and also if you find Hessian, that means second order factorization. From there you can establish that this one is a convex function. The constant is also a convex function. So we observe that our objective function is convex, our constant is convex. So simply we can say inequality constant is convex. So simply we can say that this problem is a convex optimization problem. And the graph I have already plotted it here. You can observe that. So this is the plot of this linear function, linear objective function minus 2x1 plus x2. So you can say this is the plot of minus 2 times x1 plus x2. From graph also easily you can observe that what is the curvature of this function. Curvature is 0. That means 0 is always, we can say that it is a 0 is a non-negative number. So curvature, that means curvature is always measured by Hessian. So you can say that the objective function is having Hessian greater than equal to 0. Equal to 0 means greater than equal to 0. You can say that Hessian is here. What? It is a linear function, so Hessian is 0 for objective function. Similarly, if you come across to see the constant function, what you will observe, so constant function, it will introduce a label set, because x1 square plus x2 square less than equal to 3. What you will get? You will get this label set in the domain. So what you got a disk, and what is the nature of disk? So if you this disk is the feasible set of this problem. So this disk is again happens to be a convex set. So you observe that you are minimizing a convex function over this disk. That means convex set. So that's why it is a convex optimization problem. And you have already established it also satisfy a standard form of convex optimization problem. Similarly, if I take another example, that would be an example of non-convex problem. While how non-convexity is coming, we will see it here. So consider a problem. We are minimizing a quadratic function x1 square minus x2. Our objective function is x1 square minus x2, and we are putting a constant here. This constant is equality constant. But remember that this equality constant is not a affine constant. It is a non-linear constant. If you draw this function, or what does it define? It defines a label curve in domain plane. X1 square plus x2 square equal to 3. It will define a level curve in the domain plane. And if you draw that level curve, it would not give a level set. It would be just a level curve. A level curve happens to be a always non-convex sheet. So that structure we will see it here. So here first, again, in various way you have to define convexity of your objective function. So I'm saying that x1 square minus x2, it is a convex function. Why? Because it is a quadratic function and it is having a non-negative Hessian. Easily you can find Hessian of this one. Hessian will include only coefficient with respect to x1 only. So 2, 2, 0, 0, 0, 0. So that one is always a Hessian. That one is a positive semi-reference matrix. So you can say that through second order of characterization of convexity, you can say that your objective function is convex. Similarly, if you come across to see write it like this way, minus take x1 square plus x2 square minus 3 equal to 0. So this one is your equality constants. So what you observe, equality constant, sorry, equality constant. We don't have equality constant here. We are having equality constant. So equality constant is a nonlinear constant, which means it must definitely, it will define a curve in the domain planes. So that's where the curve always happens to be non-convex. So that's with this constant, due to non-convexity of the constant, the problem is non-convex problem. Here, remember that here your objective function is convex, but your visible set is a non-convex set. So that's where this problem is a non-convex problem. So you can see the plot of objective function. This is a plot of x1 square minus x2. I have plotted all these from Academo. You can plot all these. That one is an online plotter. And the what is the feasible set? Feasible set is the this curve, this curve or this circle. This circle is what? Definitely, this circle is what? It is not a convex set. Why? If you take any 2 points from this circle, suppose this call x and this call y, and if you join the line between these 2 points, call it x and y. But you will observe that the line segment except y and x and y, these portions are totally out of the circle. So that's why circle can't be a convex set. So due to that also you can observe that you can say that your feasible set is this circle and circle is not a convex set. So that's why this problem is not a convex optimization problem. That means it is a non-convex optimization problem. One example is PCA. PCA happens to be a non-convex problem, and we will see that those things later when we will talk about solution process of this convex optimization problem. So now I would like to introduce more generalized version of convex optimization problem. What is that? It is needed when you are solving very complicated kind of problem. When you are trying to solve very complicated kind of real problem, that time these things you may need. So it is one generalized convex optimizer problem. What does it do? Here we are introducing this inequality less than equal to in place of this inequality, that we are very much similar, that we say that one left hand quantity is less than right hand quantity. We always say this. So this one is very obvious inequality. Now we will introduce for generalized convex optimization problem. We will introduce a generalized inequality. So with respect to a cone. So K is a cone. So here we will say that A is less than B with respect to this cone. It implies that B minus A is in the cone. This is the definition of generalized inequality. Even this implication, it is a definition, so by implication would be here. So this is the generalized definition of inequality. So we will change the inequality in convex optimization problem by this generalized inequality less than equal to with respect to a proper cone K. So we generalize the above constant inequality constant, allowing cone constant. So this constant we are calling it cone constant. So what is it? That means our x is also one more constant we are putting, that x is coming from a cone. A is a cone, and cone is a very special kind of cone. What cone? It is a proper cone. Just for existence criteria we are putting a proper cone. So means that what is meaning of proper cone? cone must be a convex, it must be a closed, that means it contains all of its boundary point. uh, K is having a non-empty interior, that means interior can't be a empty set. Definitely there is at least one interior point K is having, that cone is having. And K is pointed, that means K is unidirectional, that means it is having only ray, it is not having a complete line. So like this is pointed means it is having only one direction. So like it is going considering like this direction, it is not considering 180. If you rotate this vector v1 by 180 degree, what you will get, you will get this one, this vector we are calling it minus v1. So if v1 is in K, then minus v1 is can't be in K. Why? Because that one is talking about two pointed direction, two-way direction. That's where is pointed. So cone is always happen. So we try to get this kind of structure actually. So this is a pointed point, cone, and which is closed and which is pointed. Also, it contains each of its boundary point. These are the boundary of this cone K. K. Okay, so this cone is a proper cone. And with respect to this proper cone, we can define a generalized inequality. It's saying that x is less than equal to y with respect to k if y minus x is again in k. So a standard convex optimization problem with respect to this generalized inequality, we can formulate like this way. Here we have changed the inequality by generalized inequality. That is the only change. So what is happening when where you will see this kind of problem when you are solving matrix factorization kind of problem, and matrix when your domain happens, feasible set contains matrices, that semi-definite matrices kind of things. So semi-definite cone is always a semi-definite. If you take a collection of all semi-definite matrices, that means S1 Sn plus, then what does it form? It forms a cone. So if your function is defined, your feasible set happens to be this kind of things, then you have to go for this kind of problem. But we won't discuss those problems here in this course. Just for a generalization perspective, I had given it here. And here, what is the condition here? Each constant function fi must be a k convex. That means here inequality is defined with respect to k, on k. Coming to a few examples where what we will see that the problem actually is a convex problem, but it doesn't look like a convex problem. That means we need to introduce some kind of transformation to transform or reduce that problem into a convex optimization problem. So those example I will take it here. So we are taking here one optimization problem. And in between, if you are having any doubt, any question, you can ask. Otherwise, just listening is not a good habit to understand this course. So we are minimizing this objective function x1 square plus x2 square. So definitely you can say that this one is a convex function from second order characterization. Also, there are many tests. Also, you can apply line search method to establish the convexity of this function as well. And subject to constant x1 divided by 1 plus x1 square. So this function is definitely f1, this infinity constant function f1, it is a non-convex function. Why it is non-convex? So it take as a homework, what you do, define a line which is passing through origin and in the direction of 1 1. So take a line like this way, x equal to passing through origin and with a direction 1 1. So take x equal to t times 1 1, but t is a real number. That means you are stretching along a line and try to establish whether then what will happen. In that case, this f1 would be just function of t, a step size t. So you have to establish the convexity of this. So it is a just function of one variable. So f1 of t would be what? It would be just you are taking along, so x1 equal to t. You are putting it t here, and x2 is what? Also t. So you will write it here 1 plus t square. So what does it look like? It is a function of one variable. So you can apply here also second derivatives. Find the second derivative of this one. If second derivative is not greater than equal to 0, then you will claim that this function is not a convex function. And the second derivative, because it is a function of two variables, easily you can find second derivative as well. So if it is not greater than equal to 0, you will claim that your constant infinity constant function is not a convex function. Otherwise, also to equality constant, what does it contain? It contains a nonlinear function equal to 0. So due to this nonlinearity, again we can say that this one is not a affine function. So it is not a affine function, it is a nonlinear function. So due to that, here inequality is also creating equality is also creating problem. So this overall this problem doesn't look like a convex problem in a standard form. But if you try to find the feasible set of this one, so if you simplify it, what is the feasible set of this one? It says that x1 less than equal to 0. What does it mean? X1 is less than equal to 0. If you are willing to plot, where would be x1? So find the feasible set. So x1 less than equal to 0. This one is your x1 axis. This one is your x2 axis. So x1 less than equal to 0. It is talking about this portion. Now, this equation, equality equation, if you simplify, what does it give? It will, after simplification, it will take form x1 plus x2 equal to 0. That means x1 equal to minus x2. That means it is talking about a line passing through origin. It is this line, but we have to take intersected region because it is talking about end here, this constant and this constant. So what is the feasible set? So feasible set is just this ray. It is talking about this ray only. I would like to draw it here in fresh way. So this is the your feasible set for this problem. So what is ray? Ray is always a convex set. So that's why your objective function is convex due to second order characterization, and your feasible set is also, it is a ray. Being a ray, it is a convex set. That means overall this problem is what we are minimizing a convex function over a convex feasible set C. So it looks a convex optimization problem, but it is not in a standard form. So what we have to do? Yes. So first I will discuss about plot of this function as well. Then I will talk about how to reduce this. So here, this is the plot of objective function. Very nice ball shape function. So x1 square. If you plot x1 square plus x2 square, that means plot of objective function is this one. It is a ball and it is having a positive curvature. So that's why this objective function is a convex function. Similarly, if you come across to see equality constant function x1 divided by 1 plus x2 square, so what you observe? Plot of this function, it does look like this way. So what you observe? This function is not a convex. Why? Because of, you can observe here. So this, due to this portion, it is not a convex function. Even due to this portion, it is not a convex function. So x1 by 1 plus x square, this is plot of x1 by 1 plus x2 square. So from the plot, easily you can see that it is not a convex function because it is not having a positive curvature everywhere. So that's why it is a non-convex function. Similarly, if you plot this equality constant, what you observe, you are getting like this way. So it is not a affine function. So it is a plot of x1 plus x2 whole square. So definitely it is a nonlinear function. Due to that, it is not a affine function, not a affine function. So equality constant is not affine. So that's why the given problem is not a standard convex optimization problem. But if you take intersection of these two set, intersection of these two intersection of these two conditions, it will give what? It will give a ray. Ray happens to be a convex shade. And this is the plot of x1 square plus x2 square. Okay. Now coming to reduce this problem to a standard convex optimization problem. So what we do? So simply we will apply we will solve this inequality. So remember that this inequality is one-sided. That means if you solve this inequality, x1 divided by 1 plus x2 square less than equal to 0 implies x1 is less than equal to 0. But converse is not true. That means x1 less than equal to doesn't always imply that x1, because this inequality contains something more than that x1 less than equal to 0. So that's why converse is not true always. Now, further, what you do? This one was with respect to inequality constant. Inequality constant. Similarly, what you do with respect to equality constant, what you observe, simplify the inequality constant as well. So that one is simplification is also unidirectional. That means you are going from nonlinear to a fine nature in unidirectional way. So if you simplify x1 plus x2 whole square equal to 0, and simplification of this one is unidirectional. So it will imply that x1 plus x2 equal to 0, but converse is not true. That means x1 plus x2, it is not always true because it is containing something more than that. You can also observe that this one is linear kind of things, and this one is non-linear kind of thing. So it is something more than linear part. So it is unidirectional. So after simplification, you are getting this function. Now come to see here. What is x1? First, you have already seen that x1 square plus x2 square, it is a convex function due to second order characterization. Now coming to inequality constant, f1 of x, it is having only one inequality constant, it is equal to x1. So what does it define? It is a linear function. The linear function is always a convex function. Similarly, if you see in equality constant, what is equality constant? It is again talking about x1 plus x2. It is again a fine function. So that's why this problem is now a convex optimization problem. So here I have plotted again. This one is the plot of objective function, and this one is the reduced problem, which is actually a convex problem. Reduced problem of the last. Apart from that, there are many general technique of reduction. So remember all these inequalities. These are very important. How to reduce? So you have to apply concept from calculus in order to reduce a problem which looks convex, but it is not appearing in a convex form. So you need to do little bit reduction or little bit modification in order to see convex pattern of that problem. And this is the plot of function x1, f of x equal to x1, f1 of x equal to x1. That means x2 varying freely. So this is, so it is a line. It is a plane. Plane always happens to be a convex function. Now again, if you are willing to plot the equality constant x1 plus x2, again it is a plane. So plane is again a affine function. Always happens to be a affine function. So nice. So that's where this problem is a convex optimization problem. So you have to do all these little bit modification in order to reduce into convex optimization problem. So now I will talk about optimality condition, and I will talk about few things about uh, local and global optimal points. What are those? Okay, so here, if your problem happens to be a convex optimization problem, then you can say that your local optimal point is actually global optimal point of the problem. So local optimal, just you have to find local optimal point, and you know that how can you find local optimal? So if when you are dealing with gradient or Hessian, all these are uh, local concept. These are always defined in local sense. It is not defined throughout domain of the function. It is these derivative and Hessian, all these are always defined in local sense. So when you are trying to find optimal point of a problem with respect to Hessian or by using gradient or Hessian, then simply it means that you are just trying to find a local optimal point. You are not going for global optimal. And later you will come across to see that your problem was actually a convex problem. Then you can say that your local optimal becomes a global optimal. So that's where there is a very well-known theory for local optimal process, but there is no proper theory for global optimal process. Global finding global optima is one of the difficult problem. So you can't. It is not guaranteed that you will get a global optimal point, but you may get a local optimal point of a non-convex problem. So that's where this theory is interesting. And convex optimization is we are due to this we are saying that every convex optimization problem is tractable. That means you just find local and you can say local optimal and you will get that would be actually global. There is only one kind of optimal point. That optimal point is actually global optimal point. So always you will get optimal value of a problem. So and it is saying that every convex optimization problem is solvable. So due to this property, we are saying the convex optimization problem is solvable. I will talk about one result regarding this. If you are taking a function which is convex over a convex set C, and C is happens to be a subset of Euclidean space Rn, and you can simply say that C is your reducible set. In short, you can say that C is your reducible set of the optimization problem, convex optimization problem. And consider x star, it be a local minimum of the function over C. Then this x star is a also global minimum of f over c. The same x star, that local minimum is a global minimum of f over c. How? So just little bit trick to prove it. So since x star is a local minimum point, so definitely there exists a positive real number. Epsilon greater than 0, always see that there exists a smallest as small as possible positive real number. As small as possible positive real number. In short, if you are just calling it epsilon greater than 0. So if x star is a local minimum point, then there exists an epsilon greater than equal to 0 such that in the small neighborhood of x bar, this is talking about a small neighborhood, this neighborhood is close, a small neighborhood. So it is defined because I have taken close bracket. So it is defined like this way. I think you all are familiar with this neighborhood. So B of x star epsilon, it says that it is a collection of all the point of from the domain y such that distance of y with respect to x is less than epsilon, less than equal to epsilon. Equality is also coming here. So that's where this one is a closed ball. You can say that less than equal to epsilon. Y minus x star less than equal to epsilon. So this is the definition of this closed ball x star epsilon. So in this in this ball intersected with the visible set, x star is the least value. So it is defined locally because it is defined in the neighborhood. That's why we say that x star is a local minimum point. Now we will take another point y from the feasible set C, but we don't. It is y is not equal to x. It is other than x star. So and we claim that the value of function at y is greater than definitely greater than equal to this value of function at x star. And for that perspective, we are taking a theta. Uh, it is defined with, we know that y is not equal to x star, so definitely there is a distance between y and x star, positive distance between y and x star. So this inequality, this condition, when here we have taken y which is not equal to x star, it will say that the distance between y and x star is greater than 0. Remember that it is greater than 0. Equality will not come here because y is not equal to x star. Taking this property of x would be between 0 and 1, and with respect to that we are defining a new point x star plus theta times y minus x star. So definitely this point would be again in the uh, closed ball x star b of x star epsilon. How you can visualize easily? So if you find the distance of this new point with respect to x star, what would be distance? So how can you find distance? Find the distance. So this point is your new point. So and you are trying to find distance with respect to x star. That means you have to subtract this point from x star and find the norm and see what would be norm of that. So x star plus theta times y minus x star. What would be this? It would be just theta times y minus theta times y minus x. And find the norm or distance. So put norm both sides. That means you are finding the distance of the new point x star plus theta times y minus x star with respect to x star. So it would be, this distance would be equal to distance of that theta times y minus x, and theta is a positive real number. It will come out, and inside what you will have y minus star, y minus x star. Okay, you got it. So now from here, what is the value? So this is the distance between this point and x star. And what is theta? Theta, take the put the value of theta. If you are putting the value of theta, it would come like theta is what? Epsilon by norm of y minus x star. And it is multiplied with norm of y minus x star. So there would be cancellation, and that's where distance of this point with respect to x star is epsilon. That means it is, this point is on the boundary of this ball. That means boundary is also included here. So you can say that this point is inside in the ball, not an interior point, but it is a boundary point. So cancellation will happen here. It will come equal to, that means distance of x star plus theta times y minus x star is epsilon. It says that this point is on the boundary of this ball. That means this point is in the ball. Okay, so it is fine. There is no issue. So if you, due to that this point is in this ball, and x star is a local minima, so definitely the functional value at this point, function value definitely it would be greater than equal to f of x star. Why? Because x star is a local minima in this neighborhood. So due to that, if you simplify this one using Jensen inequality, you will come across that here you will get theta times, just simplify this inequality, you will get theta times f of x star is less than equal to theta times f of y. So cancel it this theta, because theta is a positive real number, so cancellation is allowed. So you can claim that here x star is the actually least value in this interval. Y can't be in the feasible set. Y, remember, y was not from this local domain, it was from C. Y was any general element from C, and we come across to C proof that y is not taking least value, while for any general y, f of f of x star is the least value. That's why this condition it says that f of x star is a global optimum point of this problem as well. So this is the proof technique. Then I will talk about few further properties of convex optimization problem and optimal point of a convex optimization problem. So what you do, if you put a condition over that f is apart from being convex, it is strict convex. If f is a strict convex function over the convex set C, then you can say that your this any local minimum x star would be a strict global minimum of the function over this set as well. Now, second property, it says that if you are taking f is a convex function over a convex set C, then the optimal points that the function may have one optimal point. For a convex optimization problem, you may get one optimal point, two optimal point, or no optimal point. It may happen. So that is if you are getting more than one optimal point, that optimal set we are calling it an optimal set or optimal set of optimal points. We denote it by either some book denoted by x star or some book denoted by x opt. It is containing all the argument where the function is having the minimum value, and this x opt is always a convex set. So in addition, if x is f is strictly convex over C, then definitely there is a guarantee that at most one optimal solution will exist, or solution or optimal point will exist. So I have taken three criteria. It is a convex function, which is not a strict convex function. So what you observe that not a strict, but it is a convex function. Because it is having non-negative curvature. So these points are all optimal points from the domain. So these points are giving x opt. So x opt is an interval. Interval is always a convex set, but it is a convex function. You need to write it not a strict but convex function. So further, I will take one function which is a strict. So this function is a strict and convex. So again, what is the name of this function? This function is exponential 1 by reciprocal function, 1 by x function. So this function is having no optimal point, but it is having optimal value, and it is a convex. So a strict convex. But if you take a function which is a strong convex, there is a guarantee that unique optimal solution will exist. So it is a strong convex function. It is having a unique optimal solution. Okay. If you have any question, you can ask. Otherwise, I'm going to wind up today's class. Regarding attendance, go and mark your attendance there in the Google